Hey, so this is a group meeting style presentation that I did about the article Microemulsions of Non-Ionic Surfactants with Water and Various Homologous Esters that I've been reading for prior to this and made some videos about that as well. And what I've done is I've thrown together a quick presentation. I mean, it took a day, um, but so not that quick, but there you'll see that there's lots of loose ends in this. I've got the article right here. So a lot of times these presentations, especially when an advisor who knows much more, a professor, a UC Davis professor, uh, is attending, they'll have a lot of questions, and they'll even know some of the answers to them. But let me go ahead and show you. So this is not a finished presentation. This is just something I threw together to advance my knowledge and my groups, because I'm going to be presenting this to my group um, as a source of information about microemulsions. And this could lead to some experiments that we're going to do. So let's see, I've got my PowerPoint here. And I will say this, it's not, sometimes they're longer than this, but this is sort of a quick and dirty presentation. It's entitled How to Make a Ternary Phase Diagram um, of a Microemulsion, because that's sort of what we're going for here. And I broke it down into three parts. What is a microemulsion? And I've got an abbreviation, micro, E. Why would I want to create a microemulsion? And how to make ternary phase diagrams, which is the point. So, and you may or may not recognize some parts from the previous videos about the journal article reading. So first off, what is a microemulsion? A microemulsion is typically a thermodynamically stable mixture of oil, water, and a surfactant. Very true. And one of the things we're interested in is using an oil, using a surfactant, and not necessarily using water. One of the reasons is because water has been used a lot. And so we have ideas about other hydrogen bonding or highly polar substances that we can use instead of water. Uh, though a classic example is going to be a water isooctane aerosol OT or AOT. Um, and AOT is this molecule right here. It's an anionic surfactant, um, surface active agent. It's got a polar head part, and its non-polar parts are sort of two on either side. Uh, and you can imagine that these sort of fold up. And so you've got sort of a head. I think actually I've seen it drawn, a head with two tails coming off of it. Um, and then here's isooctane. So this would be 2,2,4. Trimethylpentane is another name for, I think that's it, for isooctane. And water. And so we've got water, we've got oil, we've got surfactant. And when I looked this up at the reference down here, uh, I found this phase diagram from 1980 where, and this is perhaps your first phase diagram. It's got water in this corner. It's got AOT, surfactant down here. Then it's got octane up here. This is a phase diagram we'll talk more about in a second, but pay attention to the fact that we've got L2, we've got L1. Oh, L1's only way down here. We've got LC for liquid crystal. And then reading these, let's see, so I think typically this is 0 to 100% of the isooctane, 0 to 100% of the water, 0 to 100% of the AOT surfactant. And we'll talk more about how to read these as part of this presentation, and it takes some time for me. Well, here's a little more of a generic ternary phase diagram. And what we can see here is the L1, the L2. Um, L1 is how they refer to oil and water. It says emulsion. I just pulled this from the article down here. But it should say microemulsion because this is what's called a micelle, Micelle. Um, and it's got, for whatever the surfactant is, it's drawn here with a polar head and a non-polar tail. So if we were to talk about AOT, this would be the polar part. Look at all those oxygens. In fact, it's not even polar, it's ionic up here. And then it has two non-polar tails. And again, this is just a generic way of drawing it. If you wanted to draw AOT, you might draw a head with two tails coming off of it. But and this is an oil in water. It's very close to the pure water portion. It's got water and surfactant and very little oil here. Um, and then up here is what's called a water in oil microemulsion, not emulsion. Here we've got oh, I should have said this. The oil is in the micelle. Here the water is in the micelle. And you've got head groups, which are polar. They're attracted to the water. You've got nonpolar or less polar tails sticking out into the oil. And this is what's called a reverse micelle. I've also seen it called an inverse micelle as well. We've got some other things here that we'll talk and show examples of. Certainly this bicontinuous phase is interesting. We'll see a little bit more here. Liquid crystals, super excited about liquid crystals because liquid crystals are what I did my grad work on, though in a very different context. So let's see. What we can see from this is there are many phases um, that are possible in these phase diagrams. Here's another one I pulled. This one shows the L1 phase down here. It's actually remarkably similar, even though it's from a totally different source. I don't even think it references the previous one. Let's see. Oh, yeah, this one. Um, but here, L1, it makes the distinction that very close to the corner here, there's very little oil in these micelles. And then as you go along here and up to include some oil, they become swollen or they increase in size. That's the same thing that happens in the L2, the reverse micelle phase. So as you go up here, there's very little water in the micelle with the oil surrounding it. Here, there's a lot of water. And then in particular, this is the bicontinuous phase. And the bicontinuous phase, which we'll see another picture of, shows water, oil, water, and this sort of random, maybe even stochastic or chaotic pattern. It's got the same thing. It's got pure water down here, pure oil, and pure surfactant. Sometimes I think I've seen the surfactant at the top. And anyway, so these are coincidentally very similar. What else? Oh, the Windsor classification. We'll see that over here. Windsor 1 has oil on top with a microemulsion on the bottom. The microemulsion on the bottom has the water in oil. And I think that's right. Well, here we've got uh, water-rich phase with oil in water, microemulsion on top. Where do they go? This is all one phase. That's the bicontinuous. Everything is all mixed together in a microemulsion. And here we have a microemulsion with oil on top and water on the bottom. And this is called a Windsor 3. Windsor 1, 2, 3, and 4. The W stands for Windsor after the guy who came up with that classification system. Anyway, again, lots of phases. D is the liquid crystalline phase, just like it's mentioned here. And that's a whole nother topic. Here's a little different picture of, again, just a generic um, water and oil microemulsion with the water in the middle, the polar head groups, and the tails sticking out. And so this is just oil right here. Oh yeah, it says water there and oil. Good. The opposite, oil and water microemulsion. And then the bicontinuous microemulsion, where here we're starting to talk about how curvature is influencing what phase is there. So here we have what they're calling negative curvature. I didn't do a whole lot of research into negative versus positive curvature, um, but there's a balance of curvatures here for this bicontinuous phase. And shape of the surfactant is an important part of how the surfactants function and what the areas of the phase diagram look like. And we'll see some. Yes, here's the Windsor classifications. This is actually from the article that I read in the journal article reading section that started all this off. Notice that I haven't talked a whole bunch about it. I've just been pulling stuff from Google searches from other um, articles that I've read. And but again, we have Windsor 1, which has an oil in, oh, this is a water in oil microemulsion down here with oil on top. Here's a uh, oil in water microemulsion with water on the bottom. That's Windsor 2. Windsor 3 has all three phases, and Windsor 4 just has one. And is generally all, well, that's right. I was reading that the Windsor 4 could be anything. Could be oil and water, could be water and oil, could be bicontinuous. I don't know if there's any other options too, but and that's from the article, as you've probably already seen. Oh, and this is what do these microemulsions look like in test tubes, which is important because we're going to be testing them in test tubes. Why would I create a microemulsion? Well, again, the same article. There are tons of different resources for different reasons you would want one to use industrially. When I looked at them, there was just no simple way to incorporate any of these into this presentation. So perhaps that'll be a different presentation. Suffice it to say that microemulsions are useful. And the article that we were reading said you can use them to remove antidepressants from wastewater. They used tricyclic antidepressant drugs shown here. Not going to spend too much time on it, but I did want to always touch on one thing that they can do, they can be used for. What you can imagine is that if you have an aqueous phase that has tricyclic antidepressant molecules in it, you contact that with a microemulsion phase, this time with water and oil microemulsion. So let's see. Oop, keep going. Water and oil microemulsion. Wait a minute. So this is an oil and water, and this is a water and oil. Well, I've got a question right now, which is how are they going to do that? Oh, well, I know how they're going to do that. They're going to do it right here because right here is a microemulsion. Oh no, it doesn't have to. Mm, well, we'll have to think about that. Good question for later is, so how did they do this? I guess they took this, contacted with a microemulsion phase. I know they used a Windsor 2. I don't know why I have to click twice there. Windsor 2, which is this one. But they don't have, maybe I have these backwards. I didn't think so. Well, okay, so further study. All right, but then, yeah, because I'm going to talk about how it's in a Windsor too. Anyway, I'll look into that more. Aqueous phase, microemulsion. Um, the TCA molecules go into the micelles that have the water in them, and the aqueous phase is cleaned. Um, and they've shown that in their paper, they report that they're able to get greater than 90% removal of tricyclic antidepressants using PrAC, which is propyl acetate, which is shown right here. 1, 2, 3 carbons, acetate here. Bridge 30, which is this surfactant, and water microemulsions with a water to PrAC ratio of 9:1. I didn't know what that meant or how they put that together. So I actually held up the graphs on the next page up to a window and traced for, this is for PrAC. This is for this system, PrAC Bridge 30 water. And, oh, I didn't even list this. So Bridge 30 is up here at the top. PrAC is down here and water's over here. I've got the article right here. Oh, I can show you. There we go. Yeah, ester's over here, PrAC, water. So this is we're close to the pure water side. And then if I see the black dots here, those are the Windsor 2. And here is the Windsor 4. And if you want to be in a Windsor 2, it goes so nothing, nothing, nothing. Windsor 2, Windsor 4 is above this. So this is the area of Windsor 2. And you want to do it, I'm guessing, so you use as little surfactant as possible since that's the expensive part. The water, well, anyway, so that red X represents how I found out where they can be doing a 9:1 water to ester ratio that also has a Windsor 2 characteristics, because this dashed line is approximately the 9:1 water to ester ratio. I made this solid line that turned out to be, because I have a hard time reading these things, the line of 10% ester. It was not the 9:1 water ratio line. Anyway, so it turns out that that X is about the only place I can see that they could do this 9:1 ratio of water to PrAC. Anyway, how did I do that? Well, if you look at the propyl acetate, it's the pink one here, and the pink one goes like this little straight line, and then it kind of curves over. Those are the pink points. And it's also the pink points here. So I basically traced or copied those onto this plot. There was no plot like this, but now this is really, so I could label this Windsor 2, Windsor 4. I don't know what this is. That's a good question. What other areas are there on this? Because certainly these things can be quite complicated, and we're just looking, oh, we're looking down in this water region, so the corners have changed here, I guess. Compared to the one we just looked at, everything is turned 120 degrees. So the oil is down here, the surfactant's up here, and the water's over here. So we just rotated it counterclockwise. Oop. But you can see that near the water is where there's a lot of different information. So L1, that would be just micelles. And then there's something else here, and then there's Windsor 2. Yes, so the Windsor 2 is analogous at least. Again, I don't totally understand it, but that's fine. All right, so yes, this is the water section, this is the bridge or surfactant section, and this is the ester or the oil section. And we created it from the data in these two graphs. And then, how did I make the last graph? I took data off of these two. And now how to make these graphs for at least one of the substances. So the original point of this is to do the surfactant titration method. And the way they did it in this paper was you create test tubes with oil-water ratios of 19 to 1 all the way down to 1 to 19. And so let's see. So that's going to be, so the ester is pure right here. The water is pure right here. So they're basically going to go from almost pure water, so 19. I guess they're going to go, ugh, I can never get these, but let's see. I know here is 50% water, 25% water, 50% bridge, and 25% ester. So wherever you are on this graph, so if we wanted so that would be a 1 to 1, 25% water to ester, which means there's 50% of the surfactant. If I go down here, it's going to be 50% water. No, hold on. It's going to be 25% water. It's going to be 50% ester and 25% bridge surfactant. So this would be 2 to 1 ester. Anyway, these things are very time consuming for me to read even still. Anyway, but so you can systematically vary the ratios. You can then figure out how to plot them. And there's a little confusing because these show weight by weight or mass ratios, and you're measuring things out by milliliters. So you have to know the density of the components. But anyway, you add them to get 1 milliliter. You then add surfactant dropwise with gentle manual shaking until 2 clear liquid layers were obtained, the Windsor 2. You weigh or record the mass of the test tube and find the mass of the surfactant that you've added. And then you add more until you get to Windsor 4. And so if you see here, you might, let's choose, I guess, here. So this is going to be, where'd you go? So this is going to be 12.5% water. This is going to be, hold on. Come back cursor. So 50%. So that's ratio of 4 esters to 1. And then you're going to add surfactant. Hold on. Well, so you've already got some surfactant there. Anyway, you have to start. I really have to think about how to do these things, but I will spend some more time on that for sure. Anyway, you can go from Windsor 2 to Windsor 4. I mean, I get the idea that you have to go like this way because you run into it here and then you run into it there. I'm just not sure if you go like this, straight, and you have to head, all you're doing is adding bridge. So you basically have to head straight up, I think. So let's see. You start with, if you start on this line, you start with 0. Yeah. Oh, yes. You start, okay. Right. You start on this line. You start with 0 bridge. So, because you're opposite the bridge. And right here, you've got 37.5% water. Hold on. That doesn't make sense. You must have, so here's 50. There you go. 50, 50. So you got 50, 50. Here, oh, you're greater than 50. You got 67% water. You got 37.5%. Right. So you just start on here and you basically go straight up. I don't know why this takes me so until you get to that. And so you should see these lines going straight up. This one, it looks like there was no Windsor 2 at that level. Anyway, interesting to think about. And I think not that hard to construct from a procedure. Like it's very time consuming, but the procedure is not very hard, which means it's in our wheelhouse. The original paper that showed the AOT isooctane water used the lead equilibrate method, which is in quotes because I just named it that myself. Basically, put mixtures in a test tube, cap it, shake it up, leave it in, well, it says ampules, Pyrex ampules. Oh, so those are all glass. We might use plastic capped vials. I don't know. Kept in a thermostat, temperature controlled bath for 24 hours, and then look to see what phases. Use cross polarizers. Cross polaroids can see birefringence, which is liquid crystals. Can also see 1, 2, 3 phases. And what a bicontinuous phase would look like. That's another good question. Would a bicontinuous phase show birefringence? I would think not, because it's isotropic, and liquid crystals are not isotropic. And again, a whole nother topic. Might be it. Yep, that's it. Anyway, so lots of questions asked. Actually, typically during a group meeting presentation, there's a note taker just to write down the questions that come up so that the speaker and the questioners can go and do, know what to continue research on. I forgot about that till now. So I've got a video of it, and so do you, so we can review it to see what the questions are. Um, Anyway, so very interesting. He's doing these super informative, and I hope you enjoyed it. I'm going to stop sharing and end this.